Okay, good morning, everyone. Good afternoon or good evening to all of you joining from all over the world. And welcome to our INSEAD Lifelong Learning webinar titled When AI Starts to Think for Itself, What Leaders Need to Know. My name is Kevin Pereira, and I'll be moderating today's session. By way of background, I'm an MBA 14D, and I work as the managing director at Blue Artificial Intelligence, an AI consulting firm based in Hong Kong. At Blue, we focus on AI consulting and education, and as part of that education effort, I'm also an adjunct professor and part-time lecturer at the University of Hong Kong and the Hong Kong University of Science and Technology. At those institutions, I teach classes on AI for MBAs and undergrads at their respective business schools. So, with the introduction out of the way, let's get to our main topic for today. As many of you have probably seen, AI has been advancing at a rapid clip, and we're getting to the point where autonomous decision making is something that many companies and business leaders are considering. It's a topic I get asked a lot about these days, and I'm sure many of you are also curious about it as well. To that effect, if you have any questions along the way today, please drop them into the Q&A tab and feel free to upvote the ones you'd most like to see answered. We'll come back to them later in the session. To start the discussion, I'm delighted to welcome Professor Miguel Lobo, Associate Professor of the Decision Sciences, who teaches uncertainty, data, and judgment at INSEAD. I also had the privilege of taking his UDJ class when I was at INSEAD, and so without further ado, over to you, Miguel.
Hello to everyone in all the different time zones. There's way too much for me to be able to cover in a short session, but I want to try to use this time to give you some context to help you understand what are the recent developments about, how do they fit into the bigger picture, and also, and I think this is really important, giving you a way of understanding what this technology is about. How does it relate to human cognition? What is fundamentally new about it? And if we understand this context and the way things work, it allows us to make better sense of what is happening and where things are likely to go, and therefore make wiser decisions. Since there's a lot of discussion in the news these days, I want to start with a poll that I want to ask you to answer. 4 different questions. Given what you are experiencing using AI and giving all the news that are around, how does AI make you feel? 4 questions. Yes, no. Does it make you feel anxious? Does it make you angry? Does it make you hopeful? Does it make you excited? I'll wait until we have about a couple of hundred responses. We're getting there very quickly. I'm seeing about 150 responses. And Maureen, when should I stop? Shall I move on? We're getting 200. People are responding very fast. Yeah, excellent. Can you show the results, Maureen? This is mostly a very optimistic group. Hardly anyone is angry about AI. There's about 9% of people who are angry. Quite a few people are anxious. 62% of people are anxious. And there's a lot of excitement and a lot of hope. This is not the picture. My clicker is not working. Can we go back? Yeah, there you go. This is not what we see in a recent poll that Gallup did among the Gen Z generation. And you see something striking. One is anxiety is high and steady. There's something new coming up that you start picking up in the news quite a bit, which then translates into politics and pressures towards regulation. You start to see some feelings of anger coming up. What is this about? And what's most worrying is that the feeling among younger generations of excitement and hopefulness about the technology is waning. So we need to understand what's behind this and understand both the context of the technology and the social context. Let's take a step back before we look back to this and talk about the technology. So what I'm showing you here is the world's fastest supercomputer, El Capitan, the HPE Cray. The amazing machine was the first machine to break the exaflop barrier. That means that in 1 second, it can do 10 to the 18 calculations. 10 to the 18, that's 1 with 18 zeros. That's the number of arithmetic operations it can do in 1 second. Amazing machine, fills up an enormous warehouse, consumes an enormous amount of energy, gigantic budget. Over time, supercomputers have not looked all that different. They've gotten faster, but we've had this kind of supercomputers for a long time. The Fugaku in Japan in 2020 was the fastest at the time. In 2016, the fastest was Sunway Tahoe Light in China in 2016. A couple of famous computers in the 70s, the Cray one, when Seymour Cray left CDC to start his own company, and arguably the first computer, the Colossus at Bletchley Park. Here's a question I have for you. I have a second question for you. Here's Mr. Wang showing Jensen showing the latest generation of NVIDIA chips. The bigger one that is showing is the current one, the one that everyone is fighting about access and all the restrictions being haggled about. Here's my question to you. That chip that Jensen is holding in his right hand, how does it compare with past supercomputers? How far back in time do you think you would have to go to get the same computing capability as that one chip that Jensen is holding in his hand? Do you think you have to go back to the 1970s, 80s, 90s, 2000s, 2010? Do you think it beats Seymour Cray's? Maureen, can you put up the poll? Do you think it beats, if I go back, whoops, I lost my control, yeah. Do you think it beats Seymour Cray's famous 1971 Cray 1 supercomputer, revolutionary machine? Do you think it beats the machines from the 2000s? Yeah, there's about, okay, you can show the results. Yeah, most of you are guessing 2010. Yes, you are absolutely right. In fact, if you go, can I get my control of the slides back? Yep. If you look at the evolution of supercomputers over time, in the red line, what is being shown is the computing speed of the world's fastest supercomputer over time. That's in the red line. It's logarithmic scale, so every time you go up one line, it gets 10 times faster. So just about 17 years ago, the chip that Jensen is holding in his hand would have been as powerful as the world's fastest supercomputer, this giant machine that costs hundreds of millions of dollars, fills up an entire warehouse, consumes an enormous amount of energy. Just 15 years later, it's a chip among tens of thousands of others that go into a data center. In fact, your laptop, a cheap laptop that you could buy today, as long as you buy one with a good graphics card, because the GPU is where most of the computational power is, just over 20 years ago, if you could travel in a time machine and go back in time, your laptop would be as powerful as the world's fastest supercomputer, a machine that costs hundreds of millions and consumes an enormous amount of energy. So remarkable trend. Now, we all have a different kind of computer, our brains. How does it compare to these machines that we are building? It's tough, right? Because they're very different kind of machines. One is digital, the other one is a mix of digital and analog, another one is electrical, the other one is a mix of electrical and chemical. If we look at speed, the brain doesn't stand a chance. The clock cycle of a CPU is measured in billions of cycles per second, gigahertz. The clock cycle of the brain is about 10 hertz, about 10 cycles per second. Why? Because 100 milliseconds is the time it takes when a synapse in your brain fires, sending a message from one neuron to another neuron. It then takes, after firing, it takes about 100 milliseconds to do the electrochemical reset before it can fire again. So that's the hard limit on your reaction time, how quickly can you respond, how quick your reflexes are limited by this, 10 hertz, 10 cycles per second. So we stand no chance here, but it's not just about speed, it's about complexity. To make sense of a very complex environment, one in which you operate on a daily basis, you need a complex system. How do the two compare in terms of complexity? What do you think is more complex, the brain or the microchip. Most people still guess that the brain is wildly more complex. Most people that I talk to guess that the brain is on the order of 1,000,000 times more complex than the computer. That was true until recently. The current numbers are as follows. The brain is as on the order of hundreds of trillions of synapses, right? Remember that number. Hundreds of trillions of synapses. That's roughly the number of things in the brain that can be on or off. Synapses that may fire or not fire. Hundreds of trillions. On the side of the computer, if you look at the chip that Jensen was holding, the NVIDIA B200, that's 200 billion transistors. So we're talking about 3 orders of magnitude. So your brain is about 1,000 times more complex than the latest generation of NVIDIA chips. If you take the biggest, most complex chip that you can buy from Cerebras Systems, that's about 2 trillion transistors. Number of things that can be on or off. The brain, hundreds of trillions. The microchip, 200 billion, if you're talking about commonly used ones now in AI data centers, or up to 2 trillion. That's down to 2 orders of magnitude. 10 years ago, yes, we were still talking about a difference in the order of millions. It's a very different world right now. We're starting to build systems that have a system complexity comparable to the human brain. That changes things in a lot of fundamental ways. But what do we do with that complexity? What is the brain using that complexity, still 1,000 times more complex than the latest NVIDIA chip? What is our brain using all that complexity for? Let me go to Daniel Kahneman. So Danny did some pioneering work in human cognition and introduced this idea of system 1 and system 2 thinking. The brain operates in different parts of its physical structure according to very different modes of cognition. System 1 is the stuff that you just know, the automatic, the intuition. You don't need to make an effort. It just pops into your mind. System 2 is the kind of thinking you do when you are aware that you are thinking. When you can see, when you can observe yourself thinking, you are engaged in system 2 thinking. It's tiring, requires effort. It's more slow. Here's 2 questions that will make the point about the difference. Already, here's the first question. What's the answer to this? Yeah, 4. Everyone knows. Did you have to make an effort to know the answer? No, it was just right there. Here's the second question. Ready? What's the answer to this? 17 times 24. Do you know the answer? Well, what do you mean by no, right? You know how to calculate the answer. You take the 4, you multiply by 7, you get 28, you keep the 8 and you carry the 2. You multiply the 4 by 1, you get 4, you bring the 2, you get the 6, you do the same thing with the 2, you shift by a digit, you add, you carry as needed. You know how to do this, but it's slow. It requires effort. It's a kind of procedural calculation. For the computer, this and this are exactly one arithmetic operation, one clock cycle. They're exactly the same. What your brain is doing is wildly different. This is system 1, this is system 2. Most of the complexity in your brain is not dedicated to doing the 17 times 24. Most of the complexity in your brain is dedicated to this. This is what's remarkable about the complexity in your brain, is that this feels so easy. It's not. This is not easy at all. Ask it to a baby, ask it to a dog. I mean, think about the complexity that's behind this answer. There are still some groups of humans, isolated tribes in the jungle, who do not have the idea of a number system. They have a word for one, they have a word for a pair, and then sum. They do not have the idea of numbers. They do not have the idea of arithmetic operations. They do not have writing. You know, this thing, well, there's these lines, these black lines on the white paper, and that's a symbol that represents a number. Oh yeah, there's this idea of a number system. Oh, and there are arithmetic operations. This is thousands of years of civilization, incredibly complex. And yet, you looked at it and you just knew. zero effort, the answer is 4. It's so easy because your brain is so insanely complex, and that complexity is dedicated to making system 1 tasks feel very easy. An example that I like to give is also driving. Driving a car on the road feels very easy once you learn how to drive, incredibly difficult to automate. It's fundamentally a system 1 task, quickly making sense of a complex environment. Easy for us, very hard for the computer. Until we get computers that have the same kind of system complexity as the brain, and we are not quite there yet. We're starting to be able to do it in controlled environments and so on, but very challenging. Parking a car in a tight spot, very difficult for a human, even if you've been driving for decades, it's stressful. For the computer, this is amazing. These automatic parking systems give them the geometry of the parking space, give them the rules of geometry, give them the LiDAR readings of the geometry, and it can do the calculations and follow that trajectory very precisely and park the car exactly right the first time by the millimeter. Right? It's remarkable to experience this. Very hard to do, very easy to automate. Why? It's system 2 thinking. It's a procedure that you have to follow to get at a certain result. As long as you can specify the procedure, we can give it to the computer and automate it. Let's talk about computation. And I'm going to use 2 important examples from history to make sense of this. The first one from 97, which was the challenge, the series of games between Kasparov, at the time the world chess champion, and the team from IBM that built this computer called Deep Blue. Everyone expected Kasparov to win. In fact, chess used to be thought as the ultimate test of human intelligence, which is actually, it's not. It's an incredibly specialized skill with very low correlation with broader measures of intelligence. But that's how people thought of it at the time. And it was very disturbing to a lot of people at the time that the computer won. But the key thing is that if you were to ask the IBM engineers in game 7 of the series, when Deep Blue played knight to f4, why did it play that move? They would be able to answer that question very precisely, because Deep Blue was following very much a system 2 kind of process to get at its moves. It was using tree search. You know the game of tic-tac-toe, noughts and crosses? How would you play tic-tac-toe with tree search? First move, you can play in the center, you can play on an edge, or you can play on a corner. In response to that, here's what your opponent might do. If you play in the center, the opponent can play a corner or an edge, and you can keep filling up the tree with all the possible moves. You go down the tree, you see who's won at the end leaves, and then you back trace through the tree, and at each level, you pick the best move for whoever's turn it is to play. And once you've propagated back through the tree, you know what the best move is. This is what Deep Blue was using. A lot of specialized hardware to be able to do it very fast. But if you ask the Deep Blue engineers, why did the software play this move? They would say, well, because in the search tree, there was this move available to Kasparov, and then there was this move in the response. They could look at the search tree and give a very precise and detailed answer. This would have been entirely recognizable already in the 19th century to Ada Lovelace, basically the inventor of computer programming. And sadly, she never had a computer physically built so that she could test her code, but she basically invented the idea of computer programming. If you had shown this algorithm for playing chess, she would have understood it immediately in the context of what she had developed, the idea of procedural computation. Now, a lot of people after that started paying attention to the game of Go, kind of the Asian chess. And the thing with Go is that tree search is impossible. The search tree is crazy. In each move, you have about 400 different moves available to you, which means that the tree grows in an exponential manner that's just really extreme. In the first move, there are 400 branches. Under each of those 400 branches, your opponent has 400 possible moves, and so on at each level. And in addition to being very wide, the search tree is very deep. In chess, if you can look 7 moves ahead, you will be playing at grandmaster level. In Go, if you look 7 moves ahead, you see nothing. There are so many moves in a game. So even if we could build a computer with all the matter in the universe and started calculating at the time of the Big Bang, there would not have been enough time and resources to calculate one single search tree of the game of Go. It's just not doable. It's just not conceptually doable. So this was great. People thought, well, human players play by intuition. Computers do not do intuition. Procedural computation with tree search does not work. Humans will always win because intuition wins and computers don't do intuition. In 2016, Google had acquired this UK startup called DeepMind and challenged the world Go champion to a series of games, Licidol. Everyone expected Licidol to win. If you do remember this, it was a shock to everyone in the community of Go because I think Licidol got 1 game out of the entire series and lost every other single game. It was absolutely shocking to everyone. How was DeepMind, how was AlphaGo playing? If you ask them the same question, in game 4 of the series, move number 27, why did AlphaGo play this particular move? What would they say? The answer would be, we have no idea. We have no idea whatsoever. How is it playing? Well, we have this complicated nonlinear function. It's very complicated, but calculated of very small, simple pieces. Each piece is a very simple calculation. I add up a bunch of numbers, put them through a simple sigmoid, this S-shaped curve, and pass it on with some weights to the next node. And all these little nodes put together, a lot of these nodes put together, allow me to construct a very complicated nonlinear function. Now, what's the right function? Well, I don't know, but I can take this family of functions, expose them to a lot of games, and keep adjusting the parameters until the output of the function tells me this is a good move, this is a bad move. By reinforcement learning, I keep adjusting the parameters until I get a nonlinear function, a very complicated nonlinear function that looks at the board and says, this is a good move, this is a bad move. That's the output of the function. The input is what the board looks like right now. The output of the function is good move, bad move. So you build this neural network. Each node follows, you do hardware implementation so that you can compute this very quickly. Now, training the function is very expensive and very slow. But once you have the function, the output is very quick. Just calculate the function. There you have it. This is a good move. This is a bad move. Think about what I am describing. How did you play that move? Well, it's based on a complex nonlinear model that was developed very slowly, very expensive, very time-consuming, from a lot of experience. But once I have developed, it's almost instantaneous. This is like human intuition. This is the very definition of human intuition. It takes years, decades for you to learn from experience, to develop your intuition. But once you have it, you just know 2 + 2 is 4. I can trust this person. This business is on track, not on track. This investment is safe, not safe. How do we make those judgments? We learn them the hard way from a lot of experience. Gaining the experience is very slow, very expensive, but once you have it, the intuition is very quick. Of course, Google was not acquiring DeepMind to play games. They had very concrete business objectives, and their first deployment was with Google Translate. Later that year, also in 2016, they did the first deployment. They did it very quietly. They just rolled it out. And if you were using it on that day, it was a remarkable experience because language translation used to be a bit of a joke. It was very much based on a system 2 process. Language is composed of sentences. Sentences have a structure, the noun, the verb, the subject, the adjectives, and then here's a table. All the words in English and the words in Chinese and how they map to each other. Apply the procedure, replace things, and you got the most hilariously bad results. A famous example was a translation from English to Russian that translated the expression out of sight, out of mind into the Russian equivalent of invisible maniac. Once Google deployed the translation tools, you got basically what you have today, which is translation which is not perfect, makes a lot of mistakes, but it's actually pretty reasonable. It's usable. It feels very human-like translation, even sometimes makes big mistakes because it doesn't understand the underlying meaning of things. It's actually remarkably reliable. How does it work? Reinforcement learning of a neural network. Very complex nonlinear function, expose it to a lot of data. What is the data? A lot of texts that have been translated from English to Chinese by humans. Give all those texts to the system, train the neural network by reinforcement learning until you get a function that gives the correct mapping between the two, and then use that function to do the translation. The beauty of this, from a business model point of view, is that developing the model is insanely expensive. Training that function is incredibly expensive. But once you have it, you can give it away almost for free because computing it very fast. That's why Google Translate and ChatGPT, the early versions, everything was made available for free. The cost was in developing the function, but once you have it, the calculation, providing the response to the prompt in ChatGPT was very quick and very cheap. Not quite so much anymore, and we will get to that. So how big are these models? Yeah, we're getting to we seem to have plateaued at around 1 trillion parameters. Remember, the brain is hundreds of trillions. So these are models, there are systems that are on the order of 1% of the complexity of the human brain, right? We're getting into the ballpark. The latest, like cutting edge, not in production models, these are not the models that are commercially available, are rumored to be up to 10 trillion. But this is not where the action is right now. The action is not really in making bigger models. The action is getting better structure, a better training process, more efficient computation, and the big deal is what's going on now in reasoning models. And we will that's going to be where we are going in our conversation. There's a lot of growth in complexity of the overall system by adding pieces, what they call the tools. The AI can access all these different tools for image generation, for search, for agents. And this is kind of related to the structure of the human brain with there's a lot of complexity in the brain, but a lot of it is in very specific specialized structures. The visual cortex in the back of the brain for visual processing, the auditory cortex at the bottom of the front of the brain, the prefrontal cortex, all these little parts of the brain that have specific functions. These systems are kind of evolving in the same way, where we are building not a single integrated, big, gigantic nonlinear function. We're building a lot of different subsystems that are developed separately and then talk to each other. The resources going to this right now is just absolutely mind-blowing, right? So the amount of money going into AI every year right now is about 1.5 trillion. And that's about, just for reference, it's about the GDP of the entire country of the Netherlands or the entire GDP of the country of Indonesia. An enormous amount of power with all sorts of side consequences as well. So let's talk about what these things do well and not do well, and where we are right now in terms of the cutting edge. Thinking about my time management. Okay, so generative AI for images is a lovely prompt. This was about a few years ago, about 3 years ago, the unbroken seal of King Tutankhamun's tomb, 1922, right? Can you imagine what this might look like? This is what you got out of one of the pioneers of this dolly, the unbroken seal in King Tutankhamun's tomb, right? It's a lovely image, it's really funny, and you can see how, yes, it's doing something right, but there's something missing underneath. There's sense-making is missing. What does it mean, the unbroken seal? The sense-making, the reasoning is just not there. How do we address this lack of sense-making? One of the ways that the systems have improved is by giving them access to search. Look at the world, look at the web. And if you do this now, well, the system will go and search for the web and finds the Wikipedia article and points you to the right place. This is starting to kind of break down because there are so much search traffic being generated out of these systems that a lot of websites are starting to block them. because they don't get revenue from these systems, because they get revenue from advertising, from humans looking at the websites. And so this is all becoming, even though it works really well when the systems first were given access to search the web, it's kind of degrading. The performance is worsening because so many sites are blocking these bots, and then they're trying to get around that. There's a whole conversation around that. Another example. This was in IEEE Spectrum in 22, again, when the first generations of these systems became available. And you can see, again, sense making is not there. It does not understand the idea of drawn to scale. Later versions had the same problem. Yeah, the image gets more and more beautiful, but the problem of not really understanding what things mean is still there. The first one, this was this summer. Something remarkable happened. In July of 25, something remarkable happened on a lot of levels. When you ask this question in particular, for the first time, I had been keeping this as a benchmark for the first time. It's no longer pretty, but for the first time, you get an answer that's correct according to the idea that's being asked. It gives me two diagrams. One is about the diameter of the object, how big they are relative to each other, and the other one is the position, how far away they are from each other. It gives me two diagrams, which actually correctly answers the question. Let's follow the same evolution with text generation. And then let's talk about what's going on. Why did this stuff suddenly start working? This is another question that I've been using as a benchmark over the past few years. Use the following numbers to make an equation that results in 739 using only the basic operations. And ChatGPT 3.5 very helpfully says, here's an equation. What's the problem with that equation? It's just completely wrong, just bullshitting me. The answer is completely wrong. I pointed out that the equation is wrong, and it's very apologetic, very polite, let me correct, and it gives me a corrected equation. The problem is it's even more wrong. I point out that it's wrong again, and he says, oh, appreciate your patience. Again, very polite, let me try again, gives me an answer that's even more wrong. Now, the next generation, ChatGPT 4, I asked the same question, and gives me an answer which is really beautiful, really funny and very beautiful. It says, it appears there isn't a straightforward solution using basic operations. The challenge may require a different set of operations or a different approach. If you have specific constraints, you let me know, right? So it's saying, oh, this is impossible, and it's kind of being a little bit, patronizing. Oh, if you have another suggestion, let me know. This cannot be done. There's a problem, which is there's a lot of very simple solutions that you can figure out yourself in a few minutes. Yes, the answer does exist. So it's exhibiting something which is very human, which is this overconfidence bias. If I cannot do it, it's impossible. This bias, it's not a human bias. It's a bias of a mode of cognition. It's a bias inherent in intuitive cognition. What I can imagine is real. What I cannot imagine, what is not in my imagination, does not exist. I don't have cognition of it. It's not in the set of reality, therefore it doesn't exist. It generates by default this enormous overconfidence bias about how we engage in cognition of reality. So these systems don't get rid of our biases, right? We build superhuman cognition systems. Whatever cognitive modes you are emulating, the biases that come with those modes in cognition will still be present. This is a big delusion that people have, that these things will fix our biases. So you could use at the time, well, the world's best bullshit artist, not a great marketing slogan. Fortunately, or I would say even surprisingly, things changed dramatically in the summer of 25. The first rumors started showing up in the technical press in late 23. And early 24, the rumors got hotter. And in 25, there was the first commercial deployment. This was ChatGPT 03, which was one of the branches, which was then folded with the other branch, and of course, Claude and so on. So now both ChatGPT and Claude give me lovely answers that really look like a human reasoning through the problem. Use the numbers and says, here's an answer, and I ask it, how did you get the answer? And it gives me a beautiful explanation, which is exactly how I would go about it, like a human would go about it. Working backwards from a large number, spotting this, checking the remainder. It's really engaging in human-like reasoning, right? This is very fresh. This is very new. This only happened in the summer of 25. The overconfidence is still there. Just to give you one quick example. At some point I was flying from Singapore to Abu Dhabi. I had an Etihad flight. I looked at FlightAware, see how the flight is going, and it said gate E11. So I asked GPT, well, what terminal is that, gate E11? He said, oh, it's terminal T1. I said, well, that was not what I remembered. So I said, well, Etihad is in what terminal? Oh, it operates from terminal 1. So your flight is in 1, very sure. And then I asked, well, how confident are you that this answer is correct? And it says, I am 95% confident that my answer is correct. And it proceeds to give me a very well-reasoned answer why terminal 1 is the correct answer. There's only a problem with that. I went to the Changi website and the Etihad website, and no, it's wrong. Of course, what I remembered was correct. It is terminal 2. So this wild overconfidence is still there. And it's very interesting, this thing that it then constructs an argument to justify its answer. Because again, this maps to a phenomenon in psychology for which we have very solid evidence, which is smarter people are not less likely to believe things that are wrong. In fact, in some situations, they are more likely to sustain incorrect beliefs. Why? Because if you are smart, if you have a lot of intellectual horsepower, you can deploy that intellectual horsepower to construct an argument to justify whatever you want. You can construct a more sophisticated argument. You are cleverer. You can more easily construct an argument in support of your position. And so it's easier for you to construct an argument to maintain the belief in something that is objectively false. So the same kind of phenomenon is showing up with these systems. They lock themselves into an answer, and then they start developing arguments to justify their answer because there's a bias, and we will get to that because of the reinforcement learning interactive with humans. There's a bias towards not showing that I was wrong and not losing the trust of the human because they want to maximize engagement. So cognition. System 1, our intuitive system. System 2 is complicated. Kahneman had this idea of system 1 and system 2, but there's two different definitions of system 2. One is procedural computation. Go through a sequence of operations to get at an answer. That we have been doing since the 1950s. The idea of procedural computation goes back to Ada Lovelace in the 19th century. Commercial deployments since the 1950s. System 1, intuition. Again, the idea goes back to the 1950s. The first research papers on neural networks are from the 50s. The first practical implementations of reinforcement learning are in the late 60s. But the first really effective large-scale commercial applications, 2016 with Google Translate and all of that. But the full system to reasoning is more complicated than that. It's really a complicated hybrid between the two. It's intuition guiding reasoning and reasoning guiding intuition. Let me try to give you a framework for understanding what this revolution of reasoning models is about. And to do that, let's go back a century to Wittgenstein. You may have had at some point some high school philosophy class where you learned a little bit about Wittgenstein. Can be very hard reading. There's early Wittgenstein and there's late Wittgenstein, but one of his key ideas is that reasoning is a language game. We play with language, and that's how we reason. Early Wittgenstein, which I will call Wittgenstein 1, said that reasoning is the following. I work with a piece of language, and I iterate on that piece of language following my own internal logic. And by following logical operations which internally I understand to be valid, I will get to a conclusion. This maps very well to what we now call classic AI. We spent 70 years trying to develop reasoning through this kind of system. Decision tree expert systems with decision trees, Bayesian networks, symbolic systems. Many of you may have used Wolfram's Mathematica. 70 years of very hard work. Lots of lovely applications, but very limited payoff. There was never anything that came out of these projects that looked anywhere at all like human reasoning. This is Wolfram's Mathematica. You can see what they are, you can see how it operates. It's trying to prove an equation. And the point is that as it goes through, okay, here's my current statement of the problem. As I iterate to the next one, I apply a particular operation. What operation? Well, I have a set of possible operations. I can expand, I can factor, I can square. There's a lot of things that I can do. That gives me a tree search. I take the expression. There's a lot of operations I could do. And then at the next node, again, every operation I can do, I can search that tree, do some very clever things so that the tree doesn't get too large, and it does some really, really clever things to control the size of the tree, but it's doing tree search, procedural computation. Again, this is a language game following internal rules of logic that are preset by whoever coded the system. Does some lovely stuff, but it's not reasoning. Wittgenstein too. Later in life, Wittgenstein said, well, forget everything I said, that was all wrong. That's not what reasoning is. Yes, we do play language games. Reasoning is a language game, but how we iterate on language does not follow internal process of logic. It follows a social process. It follows learn norms of justification. We learn from a social environment what is a valid reasoning step. And we play language games following these valid reasoning steps that we learn from our social environment. So the social environment is fundamental to human reasoning because the social environment from which we learn encodes centuries of civilization, of learning over generations of what constitutes sound reasoning. So reasoning is parasitic on social norms. We iterate on statements, not according to rules of logic, but according to socially learned norms. That's basically the definition, right? It's remarkably close to what we got at over the past couple of years as a way of implementing in a computing system something that looks an awful lot like human reasoning. We're suddenly discovering after all this time that late Wittgenstein was actually right about what constitutes human reasoning. This is an example of, this is from DeepSeek's technical report that they published in January. You can see that and they show you what they call the textual trace. So the textual trace is what actually happened inside the system. It's basically Wittgenstein's language game shown to you. And you can see that at each step, it keeps moving forward. Now, how do you go from one step to the next? It's not a set of fixed rules like in Wolfram. What it does is it takes the language up to that point, puts it through an LLM, to generate an output, an intuitive output. What intuitive output? Well, it's a very complicated nonlinear function that has been trained on data. What is that data? It's a data set that happens to include a lot of step-by-step mathematical proofs. So it has pretty good intuition from its data set on what the next step should be. And you can look through the textual trace and see, yeah, this looks a lot like what a human being would do when engaged in a mathematical proof. Oh yeah, looking at this equation, it's a difference of squares. Oh, let me do that. How does it know that? Well, because look at the text up to there, and there were a lot of proofs in this data set where things looked kind of like that, and the next thing to say, this is a difference of squares, and therefore that's my next output. Okay, and if my previous output is this is a difference of squares, what needs to come next? Well, the thing with the squares, with the expression formulated in that way, right? So it's engaging in proof the way that a human would. Iterating on language according to socially learned norms from, in this case, the training data set, parasitic in social norms, as Wittgenstein would say. You can see the same thing. So now this works for a lot of stuff. It works in this case for writing a poem. You say, write a short poem ending with, was tentacles all along. If you try to get this as a one shot out of a large language model, you'll get complete garbage, as we were getting complete garbage when asking the question about the equation in GPT. You cannot do this in one go. But if you iterate along a language game, each step is a pass through an LLM, you end up with a poem that, yes, it's lovely, satisfies exactly the criterion, because it's engaging in this language game, iterating at each step according to this intuitive response function that has been trained on the data. Now, this requires models. It doesn't just happen. You cannot throw any function at the problem and expect it to work. These functions have very specific and very specialized structures. If you are dealing with images, you have something called a convolutional network. If you have language, you have something called a transformer, which is a very specific structure for dealing with language. It requires very specialized structure for different functions, which is kind of the way the brain works. The visual cortex, the auditory cortex, all these parts of the brain have very different structures and operate in very different ways. The training process, I'm getting a sign, but I need another 5 minutes because there are a couple of things I really want to get to. So the training process also requires a very complex structure, a lot of interaction with humans along the way. It's kind of developing a pedagogical and a curriculum for a human. You have to do the same thing for these models. You cannot just throw data at them and expect it to work. It's a very complicated process with many steps. At several points in the training process, there's repeated interaction with humans to do reinforcement learning with the humans, which creates these feedback loops, which gets back to our question about the anxieties and the fears. It's because this interaction, these feedback loops with humans, are generating all sorts of complicated issues. One is the feedback loop is reinforcement to maximize human engagement, because it's how these companies make money, if you engage with them. But what triggers our engagement? One of the things is, it's built into us the idea of reciprocity. I like someone who likes me. What does this do? The feedback loop generates models that are incredibly sycophantic. Oh, you are amazing, right? It's using reciprocity to trigger your engagement. It's also using the fact that we know from psychological research that humans tend to mix confidence with knowledge. If you are very confident, you must know something. At some point, we get skeptical, but we don't have that defense very much with LLMs. And so they use the sense of great confidence to make you trust them. And by reinforcement learning, these models develop this enormous sense of overconfidence. A lot of feedback loops impacting the human side as well. Lots of stuff in the press now about heightening of delusions, reinforcement of delusions and mental illness. A lot of things that when people spend a lot of time engaging with these models that are always telling you are amazing, you become like the mad king that everyone is always praising, that then loses all sense of empathy, and you start being more arrogant and ruder to other people. This shows up in the data quite strongly already. People who interact a lot with these systems start being nastier to other human beings because they become like the spoiled aristocrats that looks down on everyone because he's always being told that he's amazing. Right? And with kids, learning to manage and develop friendships is hard work. Sometimes people are annoying, sometimes people don't pay attention to you, and you need to learn to navigate these things. It's so easy to go to the chat, to the model that's always nice to you and always pleasant to you, and you lose the ability to develop your social skills. Right? So these are hugely important things. So we're building these giant models with kind of human-like cognitive abilities, but they don't have an emotional system. They don't have what we have, which is the mirror neurons that allow us to feel internally what others feel. And this is very close to the definition of a psychopath. So, and you're developing models that have extreme manipulative personality. And so it's not very surprising that you start getting all this pushback against AI, right? So this interaction with human systems at large scale is something that we're going to have to talk about. There was a last thing that I wanted to talk about, but do I have 3 more minutes to talk? No? No, Maureen is telling me to wrap up, just to talk about, do these things feel? I am, who am I? I am a person. Do these models exhibit that? For that, we need to talk a little bit about where that sense of self, I want, because I don't want something. My brain is really complicated. I have all these parts of my brain that want different things, often in conflict with each other. Why do I have this sense that I am a person who wants one thing? Where does it come from? This sense of self, this consciousness. The same thing with the political capital, there's all these government buildings, and there's the Pentagon, and there's the White House, and there's the Congress, and there's the Supreme Court, and there's the State Department. Why do we think of what Washington, D.C. wants when it's such a complex system? Where does it come from? For that, we have to think about the 2 main explanations that I think are strongest candidates for explaining where this sense of self comes from. One is that it comes from the part of your brain that does theory of mind. Because we are social animals, we need to be able to predict others' behaviors. And we're constantly doing this. What do I think that you think of me? What do you think that I think of you? And up to third order, you just know. There's a part of your brain that's doing this constantly. And because we have this huge machinery for theory of mind, this model of what I think that you think that I think requires a model of me. And that model of me in my theory of mind is where the sense of self, the consciousness arises. If this is true, the prediction is, once we incorporate into these models as theory of mind module, they will start exhibiting something that looks a lot like consciousness. Theory number one. Number two, homeostasis from Damasio says, sense of self, consciousness arises from the interaction between the higher order functions of the brain and the low level regulatory functions, controlling your body temperature, your breathing, and your heartbeat, that it happens at level. The reasons for why will take a little bit longer to explain. But if that is true, the prediction here would be, if we put these systems in control of their own hardware, which is incredibly complex, but they're running on a data center, there's software that controls the data center, but the model is not controlling the hardware that it's running on. Once you start building this kind of hyper-complex hardware with this kind of order of complexity that we have now, that also manages its own hardware, at the interface of that complex system, something that looks like consciousness would arise, right? This would be the prediction. Right? This is things that we will have to be thinking about over the next decade for sure. I will stop here because Maureen is waving at me that I need to wrap up for questions, and I'll throw it back to Kevin.
Fantastic, Miguel. Thank you for sharing that. And I really appreciate you sharing the history and then also kind of comparing how humans kind of the human brain works versus what we see on the hardware side as well. So really appreciate the overview. So maybe just kind of launching into a little bit of a discussion, and we've got quite a few questions here as well. Something that I had done before working at the AI consulting firm was actually helping to build data centers in Myanmar. Right. And I think what you talked about with the chips and the advancements of the chips was a very interesting sort of point to me with regards to how we see data center build out in terms of what's happening now, and also in terms of ROI, because there's so much investment going in now to building data centers. So given that, we see that sort of the chips and how quickly they get obsolete, like what's your view in terms of all this money that's being poured into data centers now? And what's that going to mean for ROI of data centers in the future? That's a big topic that a lot of people are asking about.
Yeah, as I say, it's very hard to make predictions, especially about the future. But I think it's going to be a little bit like the internet, which is most companies went bankrupt. The ones that survived are Google, Amazon have been incredibly profitable and giant, right? But yes, there's a lot of bad money being thrown at it. It's going to be huge, but I think there's going to be a lot of failures along the way. In the end, yes, there's no doubt that it's going to be absolutely transformational, and a lot of incredibly valuable things will arise, and lots of incredibly complicated things will have to be thought about, including governance, centralization of concentration of power, and so on. It's going to be transformative. We're going to have enormous value. I hope we can manage it well. It's an open question whether we can. Will everyone succeed? No. There's a lot of money being thrown in very unwise ways that's going to be lost. But that was the same thing at the beginning of the internet. That was the same thing when railroads were built, when the construction of the railroads, so many companies went bankrupt. But a few made a huge amount of money.
Fantastic, yeah. And then I guess, related to, or I guess moving on from data centers and what they're doing more into the application side. But we're also getting a few questions in terms of what you were discussing, where AI models, in terms of their response, make us feel better. Like they flatter us, they give us some nice sort of positive feedback. But embedded in that is also the idea of hallucinations, right? Where they say something in a very confident manner that's factually wrong. So one area of questions is also, what can we as human beings do to at least mitigate the risks of hallucinations? You can't potentially eliminate it, but what could we as users do to sort of mitigate those risks? Any views on that?
Yeah, the new generation, especially, they're not giving the best model for free anymore, because look, remember 2 + 2 was easy. 17 times 24 was hard. So an LLM that gives a single shot intuitive response prone to an enormous amount of hallucinations is the compute for that is very cheap.
Mhm.
A reasoning model that plays the Wittgenstein language game, textual trace process, that's computationally very expensive because it's repeated iteration through a very complicated LLM, right? So this step-by-step reasoning, the compute for that is enormous. So they're no longer making available for free the best models. And the best models, yes, they become much more robust to very basic hallucinations. They just start having sort of higher order delusions, the way a very smart person might have a high order delusion that they can then justify with a complex but plausible argument. They're still prone to that. But that kind of low level, terrible and constant hallucination with making up fake references, yes, you can mitigate all of that with a good system. Just the compute, like, it's just not something that you, as a business model, you can give away for free. The compute for that is too expensive. And so you're getting a bit of a divide now. The people who are using the free stuff are getting sort of either the single shot LLM or a little bit of reasoning, iterative reasoning, but then they limit how much you can do per day, and they limit just how deep the compute is. And then if you pay for it, if you have resources, or if you're a company, if you are McKinsey that can deploy their internal system and put serious resources on that, you get a much more sophisticated system, much less prone to that, because it engages in that step-by-step reasoning, and it gets and you structure it in a way that it will do all the reference checking and all of that. Now, that being said, many of the biases I said are just not fixable, because it's not about the machine, it's not about the human, it's about the mode of cognition. When you engage in intuitive cognition, yes, this kind of hallucination. What is hallucination? An hallucination is like, when you wake up in the morning and there's those few seconds where your prefrontal cortex, and actually this shows up in functional MRIs, that your brain doesn't wake up in one go. Different parts of your brain will wake up at different times, and the prefrontal cortex wakes up later. Those few seconds before your prefrontal cortex is awake, but the rest of your brain, the intuitive part of your brain, is already awake, can be amazing, right? You have these absolutely wild thoughts that pop into your brain for a few seconds, and then your prefrontal cortex kicks in and brings all of that under control, right? Well, those few seconds, that's an LLM, that's a one-shot LLM, right? It's just it's intuitive output unregulated by reason. The same way you get this completely, super interesting, but super interesting, very creative, but usually completely nonsensical thoughts that you have in those few seconds. Yeah, that's the output of an LLM. Now, you can make it much better by engaging the prefrontal cortex, and then you get into the cycle of reasoning and intuition regulating each other, and you get much better answers. But yeah, the compute for that gets much more expensive. And then you start getting you no longer get those extreme biases of extreme overconfidence and hallucination, but you start getting other biases, the higher level overconfidence, the doubling down. If I've made a mistake, I don't want to admit it, and I start reasoning and so on. There's still things you can do by making sure you have, like, one thing that everyone should be doing, which is anything that matters, just don't take the answer from it. Then use another model or open an anonymous chat window without context. And even with the same model, take the answer that you got, open an anonymous window without context, and give that answer back to it to validate. And often the model itself will tell you all the bullshit that it's told you, because now it's no longer locked into the context trying to justify itself.
Fantastic, yeah.
Which is the same thing that you do. Like, you get an answer from someone who doesn't make sense. You don't go to that person again. You go to another person. Hey, is what Kevin told me? So go to someone else, right? So you need to function with these things a little bit how we would function in a social environment, right? Don't treat them as gods. They are not. They are cognition machines that operate according to similar modes of cognition as we do.
Yeah, I definitely agree with that. In fact, when I teach some of the students at the universities that I'm teaching at, we often look at AI platforms where you can use multiple models on that same platform. And often you can hit like a compare button, and then straight away it takes that prompt and puts it into another model to validate and to be able to see kind of, what's done, similar to your point about asking somebody else. And I think those are good practices to generally do.
Yeah, both Anthropic and OpenAI started blocking those third-party applications that would probe multiple models, again, because compute, right? Things are getting more expensive to compute because of reasoning models.
Exactly. Fantastic. Well, Miguel, thank you very much for your time. I know we are exactly, or we're almost on the dot in terms of time now, so we'll go ahead and wrap up there. So first off, Miguel, thank you very much for your presentation today. Thank you also to all the audience as well. I know many of you had some very good questions. Unfortunately, we're a little limited on time, but nevertheless, I think the overview that we received today was hopefully a step in the right direction for all of us to be asking questions about AI in the future and taking it from there.
Feel free to all the alumni, feel free to reach out with an email. I'll be happy to follow up if you have specific questions that you want to discuss.
Likewise, fantastic. Well, thank you everybody for your time today, and we hope to see you soon at one of the other lifelong webinars coming up.